Okay, this is Physics Chapter 13, Lecture 2. We are going to be working on your own 13.6 on page 438, but I have changed the problem a little bit. I think that the problem in the book is a little bit too simplistic and doesn't really help that much on the homework, so I've made up another problem. And I want you to draw this situation. So in the middle here we have a plus 2 Coulomb charge, and then 30 degrees, at 30 degrees, and let me give you the distance here, 2 meters. Okay, that's 2 meters. That we have a plus 1 Coulomb charge, and then 1.5 meters away we have a minus 2 Coulomb charge, and its angle with the horizontal is 20 degrees. So why don't you, and we're going to figure out the force on the plus 2 Coulomb charge. So why don't you go ahead and pause the video, draw that situation, and I'll explain how to work this problem. Okay, what we want to do is draw a coordinate plane. And I'm going to put the charge we're interested in the center of the coordinate plane. So that's the plus 2 Coulomb charge. And I want to see I want to draw out the forces as vectors. So this plus 1 Coulomb charge is going to repel the plus 2 Coulomb charge. Okay, so it's up here, and it's going to push that plus 2 Coulomb charge this way. Okay, so it's going to, and it was up here with, it's 30 degrees with the horizontal there, so this would be 30 degrees. So that vector is 30 degrees below the x-axis. Now this negative 2 Coulomb charge is going to be pulling the positive 2 Coulomb charge towards it. So that vector would look something like that. And it would be 20 degrees with the horizontal. Now I'm going to label these vector A and vector B. All right, and we also need to put these angles into the 360 degree system. So if it's 20 degrees between, that's going to be 160 degrees, right? And this is 30 degrees below 180, so that would be 210 degrees. Okay, so you have to get that right, or you'll end up you'll end up getting the wrong numbers if you use the wrong angles. Okay, let's get the force on vector A. So we're going to be using all right, we'll call this force on A. It's going to be K times Q1 times Q2 over R squared. So that's 9 times 10 to the 9th. All right, Q1 is positive 2 coulombs. All right, that's that charge. And then this charge is negative 2 coulombs. So, but we have to just put a positive in there, because remember, we don't put the sign in. The distance is 1.5 meters, and we have to square that. So that'll give you 1.6 times 10 to the 10th newtons, and that is at 160 degrees. And then the force on vector B, use that same formula, 9 times 10 to the 9th, 2 coulombs, right there, but then we'll have a 1 Coulomb charge, is that charge there that's pushing it downward. That distance is 2 meters. So that is going to be 4.5 times 10 to the 9th. And that's at 210 degrees. So we're going to start with those two numbers and those two angles, and then figure out the x and y components of each in order to get the magnitude and direction of the total force on the plus 2 Coulomb charge. Okay, so I'm going to go ahead. I don't have enough room on my board to keep going. So I'm going to erase if you want to pause, and then we'll start with just those two numbers and do the rest. All right, just writing this down again, we had the force on A is 1.6 times 10 to the 10th newtons at 160 degrees. And the force on B is 4.5 times 10 to the 9th newtons, and that's at 210 degrees. So we'll go from there. So for vector A, we need to get the x component. We're going all the way back to chapter 3, but to get the x component, we would take the cosine of the angle. All right, so that's 1.6 times 10 to the 10th cosine of 160. That's negative 1.5 times 10 to the 10th newtons. And the x component of vector B, 4.5 times 10 to the 9th newtons, times the cosine of 210 degrees. And that's negative 3.9 times 10 to the 9th newtons. So to get C sub x, we add those two together and get negative 1.89 times 10 to the 10th newtons. Let's get the y components. A sub y is 1.6 times 10 to the 10th. So everything else up here is going to be the same, except you do sine instead of cosine. So sine 160 degrees. B sub y is 4.5 times 10 to the 9th times the sine of 210 degrees. Okay, those numbers are 5.47 times 10 to the 9th and negative 2.25 times 10 to the 9th. And adding those together, you get 3.22 times 10 to the 9th. Okay, so to get the magnitude of our force, we'll call that vector C, we use the Pythagorean theorem. So that's going to be, we're going to take C sub x, the square root of C sub x squared plus C sub y squared. So that's going to be negative 1.89 times 10 to the 10th squared plus C sub y, 3.22 times 10 to the 9th, all squared. You take the square root of that and you'll get 1.92 times 10 to the 10th newtons. All right, so that's one of your answers. That's the magnitude of the force. Now to get the direction, we take the inverse tangent of the y component divided by the x component. So that's the inverse tangent of 3.22 times 10 to the 9th divided by negative 1.89 times 10 to the 10th. And that'll give you negative 9.67 degrees. But I need to adjust that. Just to remind you a little something from chapter 3. We want to put this in the 360 degree, because negative 9.67 is going to be just about, about 10 degrees this way in the fourth quadrant. All right, we know it's in the fourth quadrant because x is excuse me, we know it's in the second quadrant because x is negative, x is this way, and then y is positive that way. So we know the answer will be in quadrant 2. So the adjustments that you have to make is, if it's in quadrant 1, you do nothing. If it's in quadrant 2, we add 180. Quadrant 3, we add 180. This is to your calculator answer. And if it's in quadrant 4, we add 360. So since this is in quadrant 2, again, x is negative, y is positive, then we're going to add 180. So our direction angle is 170.33 degrees. So this is a much better example problem than the on your own problem that's given in the book, where a lot of things end up canceling out. This matches your homework a lot better. So pause the video if you need to copy that down, and we'll move on to page 4 of your notes. Okay, this page of your notes is not really math at all. We're about page 439 in the book, and it's drawing electric field lines. And I'm going to refer you to example 13.3. You're going to want to look over that on page 442. If you can read through that, that's an excellent example of how to draw electric field lines. But you've got some space in your notes here that I want you to draw an example positive and example negative charge. All right, so with positive, and the book uses positive as red, so I'll go ahead and use a red marker there. We signify electric field lines as going out. All right, and the number of field lines is proportional to the charge. Okay, so the more lines, that means greater charge. For negative, we show the field lines going in. So I will link in the description box a video that shows Michael Faraday and it's a dramatic video about him discovering electric field lines. So with positive charges, the lines point outward. I'm just going through the notes here. Negative charges, line points inward. An electric field exerts a force on charged particles proportional to the density of the field lines, and the greatest acceleration occurs where the lines are the most dense. Okay, so I'll draw, when we do 13.7, I'll show you where the greatest acceleration would be. So there are 3 rules, so we're in the middle of your notes. Number of lines is proportional to the charge. More charge equals more lines. Positive lines point out, negative lines point in, and lines never cross. If you look at example 13.3, you'll see in that example that the positive charge is twice the negative charge. So the positive charge has twice the number of lines going out as the negative charge has lines going in. So make sure you look at that example 13.3. And I'll draw on your own 13.7. So we're at the top of page 443. That says 2 stationary charges of equal magnitude but opposite sign are placed close to one another. Draw a diagram of the resulting electric field. Where would a third charge experience the greatest acceleration? Okay, so we've got a positive charge. Just draw that in red. And a negative charge. And they have the same magnitude. So let's say the positive charge is 1 Coulomb and the negative charge is negative 1 coulombs. All right, so we're going to draw the field lines. So we would have something like this, going out of the positive into the negative. And where their closest proximity is, the lines are shown closer together. But as you get further away, the force weakens. So you could signify these field lines something like this. The greatest acceleration occurs where the lines are most dense. Okay, so that's how you draw electric field lines. You'll get to practice that on your homework. So based on this lecture, you should be able to do review questions. You can finish those up. You can do 6 through 10. And practice problems, you should be able to do 6, 7, and 9. All right, and I've got a special instruction for number 6. Number 6, make sure you draw the diagram like I did in On Your Own 13.6. Okay, make sure you draw out that force diagram. So that concludes Chapter 13, Lecture 2. We should be able to finish this chapter on the next lecture, so happy electric field lines.